And that's what this talk is about. So browsers are already written in C++ and have been since basically day one. But people are also starting a trend of writing websites themselves in C++. So a very brief word about the web. It's the largest open platform we have. Billions of people can access it. It's open, so it's not controlled by a single company. And for that reason, it's a very important thing, I think. And to be as useful as it is, it's carefully standardized. So there's a set of technologies that you use when you're writing a website. To be specific, you're using HTML to design sort of the content and the structure of the site, CSS for the style or the appearance, and JavaScript to do any general purpose scripting that you might need. So there's no C++ in that rather short list of languages. So what can we do? So maybe one option is to use non-standardized approaches. There are things like ActiveX, Flash with Alchemy, Pinnacle with Pepper, that each of these let you run C++ code in a browser, at least some browsers on some OSs. So none of these are standardized, but they do let you achieve the goal of running C++. But none of these, nor plugins, nor proposals for new technologies, none of these have achieved any significant amount of either adoption or interest in the standards bodies. And this is for a combination of technical and non-technical reasons that I don't have time to get into, but if you're curious, I'd be happy to talk more about it later. But perhaps more importantly, plugins are just on the way out. Browsers are slowly decreasing support for things like plugins. If you have an iPhone or iPad, you don't have Flash on it, you don't have any plugins at all. And this is a good trend. Standardization is why you can view websites on any device, basically. If we didn't have standards, each browser would have its own separate technology stack, which would be a mess. So that sounds bad. Where does that leave C++ then? So kind of one thing is, well, JavaScript is standardized. It is part of the web. So maybe we could just compile C++ down to that. And that might sound odd, but it has happened with many languages, in fact. So Java, C#, Python, a lot of other existing languages, as well as new languages designed from scratch, all have compilers to JavaScript. So you can't run them sort of natively in your browser, but they all have compilers that let you write code in them, translate it to JavaScript, and execute that. So you're still achieving the goal, just in a slightly convoluted manner. So compiling to JavaScript, I think, certainly deserves kind of a question mark at the end there, because it is odd. So let's talk a bit about why it's odd. JavaScript is a dynamic scripting language. Here is a brief sketch of a few of the quirkier aspects of JavaScript. So you might already know this, but if not, so JavaScript is dynamically typed, so you don't declare the types of variables, you just declare var x, var y, where you can have a number or a string or anything at all. And JavaScript is happy to just convert things between types. You can see the cursor there. You can add a number and a string, and JavaScript just happily converts the number to a string as well, concatenates them, so you end up with 42, a string. And there are entire websites devoted to poking fun at sort of the quirkier, weirder aspects of the JavaScript type system. And JavaScript is extremely dynamic. It has eval, so you can just execute a string as if it were code right there. And finally, JavaScript just has a lot of high-level things that you kind of expect in a scripting language, things like array literals, and of course you don't need to declare a type, so you just have a number, a string, and an object in a single array literal. You have things like for each, so functional programming style, first-class functions, lambdas, closures. So you can't declare the type of a variable, but you can check the type at runtime, so it is very dynamic. And it's definitely a weird thing to compile into, right? We typically compile into ARM assembly, x86 assembly. We compile to something lower level, more concrete, whereas here we're compiling from C++ to something more dynamic, in fact. So it's not what you typically do. But what I want to show you is that, at least from the developer's point of view, this can actually be pretty conventional. So first, just to very briefly sketch out what compiling to a native executable looks like. So this is just hello world using cout. And you just compile it with G++, and you execute it, and you get what you expect. Compiling to JavaScript using the Emscripten project can look very, very similar. So you use em++, the Emscripten C++ front end. You give it the same C++ file. You ask it to emit HTML, and it'll emit HTML plus JavaScript. And then you can just run that in your browser of choice. And here's actually the output running in this page. So these slides are actually written as HTML and CSS and JavaScript themselves. That is, this is a website that we're viewing right now. And I can actually just look at this iframe. And if I show only that, you can see this is just a website like any other. Here's the URL over here. It's just an HTML file. I could put this on the web. People could load it. It just happens to be executing compiled C++ code and showing hello world. So basically, we provide EMCC and EM++, which are just drop-in replacements for something like GCC and G++, with the goal to make the workflow as just familiar as possible. So yes, you're compiling to something dynamic and odd and strange, but really you're just asking the compiler to emit JavaScript, and it just does that, and you happen to execute the result in a web browser. So a few more words about the compiler, Emscripten, that I'll be talking about. It's an open source project. It's based on LLVM, and it basically translates C++ to JavaScript. Generally, you run C++ through Clang and LLVM, which emits LLVM bitcode. Emscripten translates the bitcode into JavaScript, and then you just execute that in your browser. So as an LLVM-based project, Emscripten kind of naturally builds on the LLVM family of projects. So it uses Clang as its C++ front end, which is good because we get the great C++ support that Clang has for new features as they come in. We just get that for free. We use the LLVM optimizer. So even though we're compiling for this weird target, we're just optimizing the code normally using all the tricks LLVM does anyway. We use libc++ as our C++ standard library. We use libc++ ABI for low-level C++ things like runtime type info. And we're currently an out-of-tree fork of LLVM, but we do hope to get upstream at some point. So if we do that, basically you'll just have an upstream LLVM, another target, JavaScript alongside x86 and ARM. It'll just be a very natural thing to have just one more target among many. And a few more words about other libraries. So we have kind of a hybrid libc. We compile big parts of the muscle libc, which is a new libc written for Linux, which is a very nice, new, clean code base. We also have parts written in JavaScript, which makes sense for a variety of reasons. For example, JavaScript has sort of its own standard library. It has things to deal with locales and time zones, so we don't really need to compile that in from C if we just have it in the browser. So we kind of try to use what we have and compile what we must. And finally, we implement things like SDL, which is a C API people use for input and output, and OpenGL, which is a 3D rendering API. We compile those down to web APIs. So OpenGL is translated to WebGL, which is how you do 3D rendering on the web, and so forth. So you can use sort of standard C and C++ APIs, libc, C++ standard library, SDL. It just is compiled down to something that executes on the web, but that's mostly transparently done for you. Okay, so we've talked kind of a bit in general. You're probably curious what this emitted JavaScript looks like. So here's we'll start with a very simple example of a function. So this is an almost trivial C++ function. It just gets an int star, it does a load, and then it calls some calc function, and it returns some value. Emscripten could emit JavaScript that looks kind of like this. So the first thing to note is that it kind of generally looks similar in that we had a C++ function, now we have a JavaScript function. So we compile some high-level things sort of one-to-one. So a function is a function. The int star p, the parameter, becomes a parameter. Of course, JavaScript doesn't declare types, so it's just p. We don't declare its type. We also don't declare the return type of the function, so we just kind of drop the types. R is a local variable in C. It just becomes var r. So again, it's a variable goes to a variable, but we drop the type. And the first kind of interesting difference is this heap expression here, which is in place of loading from address p. So JavaScript is a high-level scripting language. It doesn't have pointers. You can't just directly access memory. That's obviously not safe. So we need to represent memory somehow in a way that works so that we can compile code. And the way we do that is we just view memory as just a large array, and a read from the array represents for us a read from memory, a write to the array is a write to memory. And specifically here, heap 32 looks at memory as a bunch of 32-bit integers. So if we load from address P divided by 4, we're loading kind of 4 bytes from the right place to do an absolute read from address P.
As long as P is aligned to 4 by default.
Yes, that's a very good point, and I'm assuming you've run into that problem. Yeah, so there are a few quirks like that. Maybe I'll spend some more time on that later, but yes, there are that. We do have tools, though, like Safe Heap, which help you find these things at runtime. So it can be a bit tricky, but hopefully not too hard. So yes, so we declare memory sort of using these arrays. But aside from that, the rest of the function is actually the same. The last line is, in fact, the exact same thing. A return is a return. JavaScript luckily has bit shift, so we just have bit shifts. So really, there's a direct mapping in many cases. And we try to do as direct a mapping as we can because JavaScript engines have been optimized for things like JavaScript functions, JavaScript local variables. That's what they've been optimizing for years. But let's look at a slightly more complex example, and we'll see a bit more of the details that make this a bit different. So imagine we have this silly little C++ program here, array of 5,000 floats, and we just loop over them and add 1 to each location. Emscripten could emit something like this. So here I've written out more explicitly how we represent memory. So we declare a buffer as an array buffer in JavaScript of 32K. An array buffer in JavaScript is just sort of a binary chunk of something. So that'll be our memory. And then given that buffer, we can declare views on it. We can see it as different types. So heap F32 here will be just a float 32 array that is viewing that binary data as if it were just a list of 32-bit floats. And given that, we can look at the function main. So it looks kind of different at first glance, right? There's a for loop here, there's no for loop over here, but it's kind of easy to see how these things match up. So there's a do while here, which continues while b is less than 5,000, which is exactly what we're doing in the loop here. I continues to less than 5,000. So the loop has been kind of restructured a little, but it's obvious what's happening. The variable b is in fact the loop variable. It's incremented by 1, as we see here. So it's kind of easy to see how these things match up, but you might be asking, what's this weird or 0 thing over here and over here? So this is something that we have to do to work around some of the odd things with JavaScript. JavaScript numbers are all 64-bit doubles. There are no integers in the language. But luckily, the OR operation is declared as a 32-bit operation. So it first coerces its inputs to 32-bit. I see people laughing already, and that's the response that I'm looking for. It coerces the inputs to 32-bit values. And if we do an OR of 0, we're not changing any bits. So all we've done is forced it to be a 32-bit value. So it's kind of odd and quirky, but it works. If you do b equals b plus 1, even if the plus 1 would have made it overflow to larger than a 32-bit value, the OR 0 sort of makes it overflow like a 32-bit value, the way a native build would. So if we do the OR 0 at the right places, we're kind of putting the type on the operations as opposed to when we declare the variables. Finally, we see this heap F32 over here. So we're just loading from memory, adding 1, and then storing to memory. So that's basically the plus equals 1 from over here. And there's some computation of the offset here, but that's all fairly obvious. There's also this plus here, which again is a limitation of how typed arrays work and something we need to work around. But aside from those somewhat odd things like the OR 0, this is just normal JavaScript. So someone that knows the language well can just read this code and follow it. But it is, however, a specific style. So we've actually formalized and given a name to this strict subset of JavaScript, which we call asm.js, which has things like that OR 0 and has that use of typed arrays and array buffers to represent memory. It turns out to be useful to formalize it because it helps us to optimize the code, and we'll talk more about that later. So it is perfectly normal JavaScript that runs in all browsers, but it still is helpful to use a simpler subset of the whole dynamic language, which is very dynamic. Okay, so we've seen a bit about the code. Let's talk about the more fundamental differences between the kind of native and the JavaScript compilation model. So In C++, you're typically going to rebuild for every OS, right? You'll have a build for Mac, build for Windows, build for Android, build for iOS. That's typically how things are done. In JavaScript, a single build has to be shipped and run everywhere. When you visit a website, everyone downloads the same content. You don't get a separate download if you're on an ARM machine or an x86 machine. And this has some benefits. I mean, the obvious benefit is that you're shipping a single build, but the downside is obviously that we're preventing from doing some amount of optimization that otherwise we could have done. So we can't write any fine-tuned x86 assembly simply because we're shipping something that has to run on non-x86 machines too. C++ and C have undefined behavior. The compiler, in fact, uses it to optimize, so it's a known part of how the whole process works. JavaScript doesn't have undefined behavior intentionally, because again, people are expected to download the same JavaScript and also have it render, execute in the same way. You want everyone to see the same website no matter what device they're using. So kind of schematically, what's going on is on the developer's machine, you compile C++ into JavaScript, and at that point, there could be undefined behavior in C++, which the compiler can do as it wants with. But it needs to resolve all that undefined behavior when it gets to JavaScript, which we then ship. And on the user's machine, the browser translates the JavaScript to something that it can execute. And at that point, there is no undefined behavior. So the build we actually ship is fully defined. Another interesting difference, I think, is the security model. So typically, a C++ application will use the local system libraries. It'll link to whatever it needs in the local system. It can access local files. Of course, it might be sandboxed in some policy, but in general, it's expected to be part of the actual system that's running on your machine. JavaScript is sandboxed. So when you visit a website, you're executing JavaScript, but it can't just access files. That would be unsafe. So a JavaScript program can't really see the machine that it's running on. It's very limited in terms of what it can actually do. And this has a few implications for us. So for one thing, an application has to ship its own system libraries. If we need libc++, we need to compile it and ship it, because for one thing, we can't expect to link to the C++ standard library on the user's system. It would be the wrong architecture, and we can't even access it as a local file. So we have to ship our own. And also, we don't have access to the file system. So we actually kind of work around this, because typically a C or C++ program wants to access files, right? It's kind of very, very familiar. So we actually fake a file system in memory that people can then sort of load data into and then use normal fopen, fread commands. So it looks as if you're accessing local files, even though you're not, just as a convenience for porting. But I think it's interesting that JavaScript sandboxing helps in some unexpected ways. So we saw earlier that we implement C++ functions as JavaScript functions. So this is that little function that we saw earlier. So this is just plain JavaScript that happens to be the output of compiling a C++ function. But the nice thing is that this is just JavaScript at this point, and the JavaScript call stack is managed, so you can't observe or modify it from executing JavaScript, which means that just by compiling C++ to JavaScript, we actually get sort of for free immunity to things like some types, at least, of buffer overflow attacks. So we get kind of some of the inherent safety and sandboxing that JavaScript itself has, even though we've compiled C++ down to it. So I've kind of already mentioned types. C++, of course, has all the familiar machine types. JavaScript has just the double. However, JavaScript engines have been optimized to handle 32-bit integers well, because it's just common for numbers to be in the small 32-bit range, and then they can optimize that, and they just execute code better. So it's a nice optimization. And for that reason, Emscripten kind of targets a 32-bit machine as the architecture that it's aiming for. And sort of another concrete way to see it is that we can't target a 64-bit machine because we can't fit 64-bit integers in 64-bit doubles. You can't fit the whole space, so we have to kind of emulate 64-bit integers. And therefore, it's very natural to just stick to 32-bit integers, which JS engines are good at. Finally, among these comparisons is the performance model. So In C++, obviously, C-style code is kind of low level and concrete, and typically we can predict what kind of speed we'll get, and it'll be fast. And in C++, we have things like RAII that at least give us very good predictability in our speed, which is great. These are some of the biggest benefits of the language. JavaScript is kind of the exact opposite. So you're running in a virtual machine, a VM. You're doing just-in-time compilation of JavaScript using type profiling. So it doesn't know the types ahead of time. It kind of runs the code, sees what types it sees, and then emits something that it hopes is the right thing. But if it gets wrong, it has to de-optimize. There's garbage collection. So there's a lot of things that can go right or go wrong, and it could be fast, it could be slow. It's just very unpredictable inherently, almost. But I would argue that this would be a big problem for us. So we're compiling C++, and we have expectations of what happens when we compile a C++ program. So if we can't get at least predictable, good speed, then this would be of limited use. So let's talk a bit about speed. So JavaScript historically began as a rather slow interpreted language in the 90s. It just had a very simple interpreter. And actually, that's about the same speed it had since the late 2000s, and that was good enough for everyone. But then the browser competition competition in the browser space heated up quite a bit. And then browsers introduced type specializing JITs, that is just-in-time compilers that see the types and, as I said earlier, emit machine code that tries to do integer math when it's integer math, etc. And they're especially good at implicitly statically typed code. So of course, you can't declare types in JavaScript. But if you're implicitly writing typed code, that is, your integers are not mixing with strings or lambdas or anything else, just using integers with integers, if you're using your types in a clear, coherent way, it's easy to optimize. And let's see that concretely here. So here's a JavaScript function, add, which gets two parameters and just adds them. So at this point, when we're just receiving the parameters x and y could be anything. They could be strings, they could be lambdas, objects, they could be numbers. We have no idea what they could be. But as we saw before, the OR 0 operation forces something to be 32-bit. And if we do x equals x or 0, and the same for y, then when we get to the last line, we know the types of x and y. So if we know that x and y are integers, and we have this OR 0 on the output, the inputs are integers, the output is an integer, so we can just emit 32-bit code there. So this is much, much easier than the typical problem a JavaScript engine needs to optimize. It doesn't need to guess at the types. It can actually, just by reading the code, it can see what the types are. And that is basically what asm.js is. It's a formally defined subset of JavaScript. There's a type system for it, so you can actually check if your code falls within the subset, where all the operations are clearly, just by looking at it, obviously statically typed. So it gives the JavaScript engine the option of even doing ahead-of-time compilation of the code just by reading it and seeing, well, this has to be an integer, this has to be a double, etc. So even though we're running in a very dynamic VM, we're trying to simplify the problem as much as possible to give it a chance to optimize. And another crucial thing for perf is memory access. So we've seen before that we represent memory as kind of an array buffer, just a blob of binary data, and then we declare some views. We can view those bits as 8-bit integers, 16-bit integers, 32-bit integers, and then reads and writes are just reads and writes from those arrays. The crucial thing is that a load in C++ then becomes a read from a typed array, as we see here. This heap 8 is basically a read of an 8-bit value. But that can directly become a load in the machine code that the JavaScript engine emits. Why? So as I said a few times, JavaScript is extremely dynamic and hard to optimize. But it has this one corner of the language that's easy to optimize, and those are typed arrays. So we rely heavily on that one aspect of the language where you can actually declare types with these typed arrays. And when the JS engine sees heap 8, it can actually emit an 8-bit read. And finally, when we represent memory in this manner, we're actually seeing it at the very lowest level the same way that the LVM optimizer does. That is, memory is just one large, flat space. and it aliases, so you can read two 8-bit values and combine them with a shift, or just read a single 16-bit value and you're seeing the same thing. So that's how the LVM optimizer sort of sees it at the lowest level. And we see it the same way. That is, we've managed to reproduce that model in JavaScript, which means that we can just run the LVM optimizer freely, and all the speedups that it can give will not break us. OK, so we've seen some positive things on the last few slides. We've also seen a lot of negative things on the previous slides. So where does speed stand currently? So here are some numbers. We'll just zoom in. So there's a comparison here between three compilers, Clang 3.5, GCC 4.8, and asm.js running in Firefox. Lower numbers are better in all of these graphs. And it's all normalized to Clang, so 1 is Clang and lower is better than Clang. And on the left here, you can see 4 kind of micro benchmarks, which are things like Fencooch and Fasta, which you might recall from the Shootout website. And on the right are more realistic, larger benchmarks, things like Box2D, the physics engines used in Angry Birds, if you've played that. Bullet, a 3D physics engine used in many 3D games. The Lua VM, and the zlib compression library. So at a quick glance, you can see that on these smaller benchmarks, there's some variability. That is, we're basically at native speed on Fencooch, but we're slightly more than 2 times slower on Fasta. And this kind of makes sense on these smaller benchmarks. A single loop or a single thing that you get right can make all the difference. But on these larger benchmarks, the picture is much more consistent and predictable. So we're at about 1.5 times slower than native, or 2/3 of native speed. So obviously we'd like to be faster, but this is already fairly close. It's much closer than you would expect a dynamic language like JavaScript to get, and it's also in a fairly predictable range. So even if we are at fully native speed yet, we are getting there. And this is one of those benchmarks, Box2D, shown over time. So the x-axis is time. It's May of last year, so a year and a half ago, to like last week, or I guess 2 weeks ago at this point. And so time is heavily compressed in this range, and then here it just shows a few days. But what you can see here is, and again, lower numbers are better, like we saw before. You can see Chrome, Safari, and Firefox overall getting clearly better till after the last year and a half. They're all kind of in this range here, so they're not all quite as fast as native, which is in the light gray at the bottom. But they're all very close to each other. That is, competition in the browser space forces everybody to get faster, and no one likes to be the one slow browser. So there's a strong trend to getting faster in this space. So overall, we're at about 50 to 67% of speed, but still getting better. There's still a lot of work going into JavaScript engines to make them faster. There are a few missing pieces like SIMD, which really matters a lot on specific benchmarks, but SIMD is actually being standardized for JavaScript now, so we'll be able to get those speed ups eventually. And I think the crucial thing is that even though we're not at native speed yet, we're already fast enough to run a large set of applications, even things like games, which depend heavily on being fast. And in fact, the game industry has been an early adopter of this approach of compiling C++ into JavaScript. So all of these engines listed here compile a large C++ code base to JavaScript and run it on the web, including on the first line, Unity and Unreal, which are probably the 2 biggest in this space. And there are products shipping right now. So they've been very, very eager to do this because for a games company, they just want to ship games and let people play them. Having the user need to download and install an app is just something in the way. They want to just give people a link and let the people click the link and just jump into the game. That's the optimal thing for them. And executing the game as JavaScript is the best way to do that, I think. So here I'd like to show you a quick demo. So again, I'm just running in a browser with all these slides, and I can just click on a link to this game here. And I don't know if you can hear that, probably not. But in any case, this is a Unity game. It's a few 100,000 lines of code compiled into JavaScript. And the takeaway from this is that it basically looks just like a native game looks, right? It's if you didn't know that you were running in a browser, you probably wouldn't think about it. Anyway, I don't know what I'm supposed to do in this game. But the point is that you can actually run like hundreds of thousands or millions of lines of code compiled to JavaScript, and you can't even tell that you're running in a browser. And that's really the goal that we have, and that's why the games companies are so happy with this. So I think the adoption and the use in products that are shipping shows that even though JavaScript is a weird thing to compile into, the results can be pretty good. And so we kind of aim to get that in a few standard ways, like we do fuzzing using csmith, and we're currently actually not aware of any bugs that are specific to our tool chain. And I think there's also a fundamental benefit for us in that you generate a single build that runs everywhere. So you emit one JavaScript file, and of course you do need to test on different browsers because, sorry, let me just finish the sentence. You do need to test on different browsers because they have differences, but you are testing a single build generated from a single tool chain. So you've at least limited some amount of variability between your builds that otherwise, if you have a Windows build, a Mac build, an Android build, you would have had. So, yeah.
Sorry, what is fuzzing?
Oh, sorry. Yeah, I should have said that. So fuzzing is when you basically emit a large number of random programs, and you just do that fully automatically. So you can generate thousands, millions, hundreds of millions, and you just run it through the compiler and you see what happens. So what we specifically do is we just generate this huge amount of programs, and we run them in a native compiler, and we run it through our compiler, and we see if there's a difference. And if there is, then it's probably our fault. So basically, fuzzing just generates like a long list of bugs for people, and you fix them. Okay, so as I said earlier, Emscripten uses Clang as its C++ front end, which means that we get for free sort of all the C++ features that Clang has support for. But kind of one trickier aspect is exception handling. So exception handling we don't just get for free. We can't just easily have that. So let's talk a bit about that. So Emscripten supports C++ exceptions differently. So here's a very simple C++ function. The simplest, I guess. It does just a try catch, call something. If it threw, just handle it. So let's see what that would be compiled down into. So here's the JavaScript. It starts out with this invoke call, which seems odd. But it basically calls something, this function, through a function pointer. So 10 is just a number that in some way refers to something as its target. And invoke just calls that function pointer and checks if something was thrown. And then we can call getThrown to see, hey, was something thrown from the last line? If it was, we check if we can handle it, which we give the thrown object and sort of a pointer to the type that we're checking, which in this case is this type with a capital T. If we can handle it, we call handle just like in C++. If not, we just do another throw and it propagates outwards. So this is kind of like we're almost not compiling anything, right? It still kind of looks high level. So let's see what those runtime functions do. So the first one, which I mentioned, was invoke, which basically gets a pointer, a function pointer. It sets a global variable to 0, that is, it assumes nothing was thrown. Then it does a JavaScript try catch over here. And it does dyn call. Dyn call actually does a call of a function pointer. And if it caught a JavaScript exception, it stores that in that global variable. So when you exit from invoke, you've called that function, and you might have caught something. And if so, you've stored it, and you can grab the thing that was thrown. The function can handle is something we need to call into some compiled code. That is, JavaScript has no understanding of C++ types. So we just compile the relevant parts of libc++ ABI, and we just give it an object and a pointer to a type, and we say, hey, can this type handle this object? And finally, do throw, which receives a pointer and throws it, literally just does a throw of a pointer. So we implement C++ exceptions using JavaScript exceptions. And I think this is kind of nice because the JavaScript language has exceptions in it. So it already has all the code that it needs to support stack unwinding and so forth. So we could somehow implement that ourselves, but I think it's just simpler for us to just reuse the stack unwinding in the JavaScript engine. So all we do is just wrap around JavaScript exceptions, including a call to whatever libc++ ABI internals do the very C++ specific aspect that is where C++ and JavaScript exceptions differ. Sort of a downside of that, though, is that our performance depends on the performance of exceptions in JavaScript, which historically has been very variable. Oh, sorry, there's a question.
Do I understand that you generate a cascade of function calls to simulate embedded catch blocks?
Yes, that is if you have a catch with multiple functions in it, you would kind of do a try catch for each one separately. We could optimize that, but conceptually it should be the same amount of try catches as you have.
It doesn't influence the kind of code we're going to write when we use that, because there is a performance implication there. Since you could have listed function calls, instead of a single set of catch blocks, it will influence the way to write code.
So the question was, I think the question was, tell me if I'm wrong, that this could cause a performance issue because when you have these try-catch blocks, like in certain places, you'll want to write code in a way that kind of avoids exceptions.
If I have a try with a set of catch blocks, I have to know it's going to result in a number of function calls in the generated code at the end.
Yeah, true. So. Yeah, so the question, which I guess ties into that well, is what happens with RAII if you have just an object on the stack and it has a destructor? What happens? So yes, I mean, under the hood, LVM and Clang will emit code that does like something like a try finally, so it will call the destructor. So we would have something similar to this code here, but without can handle. That is, it would just call this invoke, which lets you execute a function and keep running even if it threw. And yes, you could have multiple calls in answer to the other questions. So certainly this will emit kind of several runtime calls per try-catch block, and there are potentially perf downsides. A specific perf issue that used to be in JavaScript engines is that anytime a function had a try-catch in it, it would literally not optimize that function at all. So at least by putting the try-catch in an invoke that is in a separate function, we've limited the scope. But actually, JavaScript engines have gotten better. So this is actually not quite as bad as it used to be. So there is variability there. So even though on most sort of simple things we have very fast speed that's fairly consistent, when you use something like C++ exceptions and we depend on something like JavaScript exceptions, performance can be a bit more variable. Okay, so I guess I'm a few minutes earlier than I thought I'd be. So let me just briefly summarize and then can turn to more questions. So what I've been saying is that you can compile C++ into JavaScript. You can take an existing C++ code base or write a new one and just compile that to JavaScript and run that on the web in a way that's both fast and standards compliant. That is, it'll run well and it'll run anywhere the web can run. I've also talked about why JavaScript is a weird compiler target for multiple reasons. I hope I've at least managed to also show that it's kind of a fun target, at least for the compiler writer, and that you have slightly different puzzles to solve, and it's kind of an interesting thing. So anyway, it's a weird target, but I think it's also a fun one. And that's it. Thank you for listening. And yeah, questions. Maybe we should use the mic, though. I think, because then people will hear it on the recording. If that's okay.
Hi. So you mentioned a lot about performance, but are you optimizing for a specific kind of workload? You seem to be doing a lot of games and floating point heavy things, but what about like symbolic applications that involve a lot of memory allocation of small objects and integer computation?
So I mean, it is, so the question was, are we optimizing for sort of a specific type of workload? I've mentioned games a few times, and that's kind of an obvious tell that that's what we've been doing. And to some extent, yes. I mean, we do optimize for the things, the use cases that people come to us and things that people care about. However, we've also tried to sort of get realistic code bases from as many partners in the industry as we can. And we hope we're getting something that's representative, but it is probably skewed towards games just because they've been kind of focused on this as early adopters. However, games they do everything from floating point math to AI, which can use very different types of code, to rendering. So I think games, I mean, obviously it's one thing, but they do have a wide range of types of computations. So I hope that answers the question.
You should
Yeah.
probably mention that performance is largely affected by how much data you are pushing between JS and original C++. Like if you need to pass the data from C++ to JS, you need to populate your heap arrays and then copy them in native JS types like strings. And that's where performance gets stored.
Yeah, actually, I actually had some slides on that I thought I'd use if I have time, and I guess I can mention briefly now. So as the comment was just made in the audience, one of the performance pain points is when you're copying data from C++ to JavaScript, or vice versa, because the languages just see memory differently. So there's a very simple example over here where we have this compiled code function here. And the important thing is that it can only see this heap 8 array, because that's all memory is for a compiled function. It's just these typed arrays. But if getInput receives a normal JavaScript array, then array is a distinct object than heap 8. So we actually need to copy, and there is some pain there. So if you are doing a lot of I/O, that is, you're copying a lot of data between the languages, this could be an issue for speed. I mean, you'll end up doing a few extra mem copies, which is not the best thing, but yeah. So thanks for the comment, and thanks for letting me use that slide. Sure, other questions? Oh.
How does concurrency work? Like if I did threads in C++, how would it end up in JavaScript?
Yeah. So the question was about threads. So JavaScript, as you said, doesn't have sort of native support for threads. It has web workers, which do not have shared memory, and this is obviously an issue with the language. So right now, typically you compile a single-threaded application. So for example, the Unity game that I showed earlier, I think it's natively using 2 threads, but they have an option to build it so it runs everything on the main thread. That's kind of the current state. But there are some talks in the standards bodies about, well, maybe we should add threading in some way to JavaScript. And there's actually work on a prototype being done right now in the Firefox dev group. So we have like simple examples of things working. But this will be a long sort of process towards standardization. So right now the answer is single-threaded.
One more.
Oh, sure.
How would I write C++ code with Emscripten that interoperates with the existing body of JavaScript code? Is that an option, or is that a scenario that Emscripten allows?
Yeah, so so the question was, how do you connect between JavaScript and C++? And there is a talk by Chad who's sitting there. Could you tell us when the talk is? Yeah, so there's a talk about a tool that he wrote basically that does that connection. So we definitely do care about that use case. A lot of people want to compile just a specific thing and just use it within an existing JavaScript app, or vice versa, use some JavaScript from a large C++ app. Sure.
My question is about, you mentioned some benchmarks, and I assume you measured the time from when the code actually starts running to the end of the benchmark. But can you give any sense of how long it takes between the I don't know, JavaScript engine receiving the compiled into JavaScript code and when it actually starts running?
Yeah. So the question was, do the benchmarks that I've shown on this slide here, do they measure just execution time or also sort of startup and compilation time?
I assume they just measure execution.
So actually it's a mix. In general, all these benchmarks include everything so you're starting up a new JavaScript process in the shell, it's parsing the code, it's optimizing it. So these runtimes include all the compilation time, which is actually quite fast, certainly on these smaller benchmarks over here. In practice, this is variable between engines. So Firefox will do ahead of time compilation when it sees asm.js code. It uses multiple cores to do that, so it is compiling sort of in parallel. And on the Unity game that I showed you, I believe it takes somewhere between 5 to 10 seconds to do a full compilation of everything. Whereas you saw it just started up instantly for me just because it happened to be cached. So there is some compilation time. And on a different browser that doesn't do ahead-of-time compilation, it'll sort of compile in chunks, but it'll be kind of more spread out over time. So there is certainly some overhead from compilation time and parsing, but it actually is included on these benchmarks here. And in general, I don't think it's that bad, except for the really, really big code bases, maybe. And even there, we have some ideas about ways to fix it. Does that answer?
Yeah, thanks. And I think it's quite impressive that this includes the compilation time. And another question, what about debugging? What if something doesn't work out? I guess you just end up in some funny looking JavaScript.
Yeah, that is, I mean, definitely scary because this is kind of this odd, unfamiliar maybe thing. So the question was, what do you do when you need to debug some issue? And sort of there are two parts to that. One is we provide a bunch of compiler options that make it easier to detect problems. So someone mentioned from the audience that if you do an unaligned read from memory, you get something wrong. So we have a compiler option called safeheap that just checks if everything at runtime is actually aligned. So we can catch a huge set of the differences, a pretty small set of things that are different from us than a native build, but we have an option that lets you catch those small risky things. On the other hand, if you just want to debug normally, the nice thing is web browsers have a full suite of dev tools in them. All of them do. So they even have a debugger for JavaScript. And we have an option to emit what's called source maps, which basically connects a line of compiled code to the original C++ source code. So you can actually fire up the JavaScript debugger in the browser, which normally you would use to debug handwritten JavaScript, and you'll actually see C++ in there. So it doesn't have like variables and C++ types, so it's still a bit raw, but at least you're seeing the source code in the right place, and I think it's kind of helpful. And in practice, I would say the typical way people debug this stuff is just having sort of a parallel native build and a web build, and sort of generic bugs you just debug in the native build with your familiar debugger, and you just fall back to source maps or to those compiler options when you suspect it's something specific to the web build. And in practice, I think that works out well.
Thanks.
Cool. Yeah. Any other questions? Oh, is that a line there? Oh, sorry. Didn't realize. Oh, go for it.
So on the slide where you were describing that a load from a pointer becomes simply a machine load, are there any optimizations in JavaScript that eliminates bound checks, and how much time is spent with bound checks?
Yeah, so the question was, so we saw that a load in C++ becomes sort of a load in the machine code, but are there bounds checks? And it's a great question because there has to be a bounds check at the semantic level. JavaScript is a safe language. You can't read out of bounds from an array. In practice, there are a few ways that JavaScript engines can get rid of them. So in Firefox, very specifically, if you're running on a 64-bit machine, it does this trick where it just allocates 4 gigabytes of address space, and then all pointer accesses are within that, and it uses mmap to make sure that you're within bounds, so it actually ends up being free. So there's a way on at least some architectures and some if the OS lets you, to get rid of the bounds check. But more generally, like on ARM and 32-bit, and it could be different on other browsers, of course, you might have bounds checks. But JS engines are quite good at, if you have something like a loop, it might do range analysis on the loop variable, and it might be able to see that it can eliminate some bounds checks. So yeah, so there's like a whole set of things that JavaScript engines do well, which is getting rid of redundant type and bounds checks. So we kind of benefit from that.
In your examples, you frequently had small functions going into a small function. So what kind of optimizations do you allow for LLVM to do? Or will it end up with inlining like everything, eventually giving you very, very huge fat functions?
Yeah, so the question was what happens with inlining, because the examples that I showed were all kind of tiny things. Well, yes, I mean, we run the LLVM optimizer normally, so it tends to inline, and you often end up with like functions of 100,000 lines of JavaScript, and it does run fast, but I mean, there's downsides to those functions too. It can be harder to debug, so if you want to debug, you typically disable the inliner. But I mean, inlining gives the same benefits as it generally does, so we do need it. It gets rid of call overhead.
Thank you.
This will be quick and it's quite small. Actually, it was one of your very first slides. I think slide 3, perhaps. The one where you're showing floating points, floating point accesses. The raw array was declared with a size of 32K, although there were 5,000 floats. Is there a reason for that, or is that just?
Oh, did I get the number wrong?
Well, it should be. Would it be 20,000 in the real implementation?
Oh, in that sense. So it's kind of preferable to have the array size be sorry. So the question was, why did we have a 32K array here when it would have been enough to have like a 20K one? The reason was we kind of prefer to do a heap size that's a power of 2, because that tends to be easier for the browser to optimize. It can do some tricks with masking. So we don't have to do that, but it's kind of preferable to use a heap size that's kind of a natural power of 2. So that's basically the only reason. Go for it.
So in another one of your slides, you had mentioned that you lowered from LLVM bitcode directly to JavaScript. What are the advantages of doing that over lowering from Klang's intermediate representation? And that way you might be able to exploit optimizations in JavaScript engines that know how to understand JavaScript objects.
So before I repeat the quick question, could you maybe clarify what you mean, like you're comparing two things? What were they?
Right, so you take LLVM bitcode, translate it using these global heap arrays, and emit asm.js. Another possibility would be to take the intermediate representation in Clang, Clang's typed AST, and emit more JavaScript-looking JavaScript that perhaps maps, just as you map onto JavaScript exceptions, map C++ objects onto JavaScript objects.
Right. So the question is, why do we do the translation at this kind of low level of LVMIR, which is kind of at a very, almost a machine level, just abstracted away from the hardware, whereas we could have done it on, say, the Clang AST, which would have been high level, and we might have even been able to map like a C++ object to a JavaScript object, et cetera. Is that the question?
Yes.
Yeah, so there's, I think, two parts to that. First is that we did try that approach originally, like a few years back. It is substantially faster to use typed arrays, simply because they're so easy to optimize by the JavaScript engine. Normal JavaScript objects are optimized well, but using a large set of heuristics and things that change between browsers are just very hard to get predictable speed. And each of those objects is allocated in the garbage collector. So you have allocation issues and GC pauses. So that's one issue. But I think the interesting thing is there's another compiler from C++ to JavaScript called, they just renamed it to Chirp, C-H-E-R-P. I don't know why they call it that. Do you know what
it was called previously?
Duetto.
Okay.
So Duetto/Chirp is basically does what you said. They still translate LVMIR, I think, but they do it at a higher level. And they do actually emit for every C++ object a JavaScript object. Their performance is not that good because of it. I mean, maybe they'll get better over time. But I think it's an interesting approach, and it might have some benefits in some areas. Overall, though, the overhead is going to be quite high in my experience. So mainly it's completely a performance issue for us.
Are they targeting different kinds of applications?
So the follow-up was, are they, this other compiler, was it targeting other types of apps? Not to my knowledge. That is, their demos include things like physics engines, just like us. So I'm not entirely sure why they went that route. I suspect they just like the elegance of their approach, which I can certainly see from an aesthetic point of view. But from a performance point of view, we've measured it. It's just, yeah, it's just not the best way if you just care about speed.
Okay,
yeah,
thank you very much.
Sure.
First of all, I would like to thank you for developing Emscripten. We use Emscripten in production environment at Autodesk to compile our application to web, and it worked impressively well. It just very few problems. We never expected it to work so well, and we push it to maximum memory to see how fast it works, how big models it can handle, and it's very good. A couple of questions.
Happy to hear that.
First, you mentioned some compile time switch which would generate the code which would detect not aligned pointers. What is that? Can you?
So the question was, what were the options that you can use to detect like unaligned reads? I can just give you a list later, but if you have a good memory, it's just safe_heap.
Okay.
But I can tell you later.
Remember.
Yeah, pretty safe, and that checks for basically any difference between how we treat memory and how a native build does, which is mainly alignment, but also like reading from 0 actually doesn't segfault for us normally, but with safe heap, it does. So it's a useful thing for debugging.
Because serialization code, you're serializing some complex data structure which includes doubles in short jars, and it will save it in non-aligned addresses, and then you read the serialization chunk, and it does need to read it. So we're now if dev our platform is Emscripten, then we do manual byte by byte reading and assembly. But if Emscripten could do that, detect non-aligned pointers and then generate less efficient code, it would be much better for the users.
Yeah. So there's actually a few other things to consider here, but maybe let's talk about it offline, because there's a few other ways to solve that I'd like to tell you. I just want to give the other people a chance to ask.
Thank you.
But yeah, let's talk offline.
Second question. I believe that asm.js optimization is disabled if you are setting up growing memory. So only fixed memory model supports ASM optimization. Are there plans to allow asm.js for growing memory?
Yeah, so the question was, there's currently a limit in Emscripten where if you change the size of the heap, it'll actually not emit fully validating asm.js code, which means it'll run more slowly. Yes, there are plans. Actually, we're hoping to get to that fairly soon, to add an option to do a resized heap in asm.js. But I can't say when. It depends on standards bodies. But we're going to try to get it soon.
Thanks a lot.
Sure.
So as far as I know, the standard best practice in C++ for exceptions is the philosophy is try catch is free but throw is expensive. I'm wondering, with the quirkiness of the JavaScript exceptions, what are the best practices for best performance when using exceptions?
So the question is, what are the best practices for using exceptions in JavaScript? And the answer is, don't use exceptions. But no. So we hope to. So once all browsers are fairly fast at like a JavaScript try-catch inside a function, which, as I said, right now they just sometimes de-optimize the whole function, which is terrible. Once they are at that point, we'll just emit a try-catch inline in the code, just like in C, and then the browser could, in theory, have zero-cost try-catch. So we do hope to get to that point. It's not a lot of work for Emscripten to do, but the JavaScript engines, the browsers, will need to optimize it. So I would say right now exceptions do add like a few runtime calls, so they add significant overhead. Might take some time, but I hope not years, like maybe months or so, where we'll start to see fast speed there.
Okay,
hope
thanks.
so.
I'm also wondering, could you give a quick word about maybe a difference between signed and unsigned integers? Like, is there a quirk around there? Overflow.
So the question is, what happens with signed versus unsigned? So JavaScript actually happens to have a way, so I guess timeout, but I'll just finish this. JavaScript has a way to force a number to be a 32-bit unsigned value, not just a 32-bit signed value. So we can actually support both signed and unsigned values and comparisons and so forth. So that's, I mean, we basically get that info from LVM. So that's not an issue at all.
Thank you.
Yeah, cool. Thanks. So I guess there's no time for the other questions, but feel free to ask me later or grab me anytime. Thanks.